Pooled testing, relevant pre-algebra and algebra virus mathematics. We have created an 8 to 10 day lesson sequence that provides students with accessible and relevant mathematical topics connecting to virus testing. Our materials explore paired testing to identify the presence of a virus. This begins with the idea of combining two samples and testing that combined or paired sample for the virus. We start with the fundamental questions: what is paired testing? How does it work? When would there be 1, 2, or even 3 tests needed to identify the presence of a virus? Under what conditions is paired testing a good choice? We start off with a simple scenario where 25% of the population is infected with the virus. Our key question here becomes: would paired testing make sense in a 25% infected population? We explore a concrete example of paired testing. Students create simulations of trials using uncooked pasta. We color a fraction of the pasta to simulate a population where 25% are infected. Students can create a kind of brown bag urn where 25% of the pasta is red. The red pasta represents people who are infected with the virus. Students are now ready to walk through the simulation of randomly selecting person 1 and person 2 for the first joint test. We can also ask whether or not replacement has to occur when we're dealing with pasta in a bag to simulate a population. After running through a set of trials and collecting data, we can now consider the question of whether pooled testing was a good choice. Was it more efficient to use paired testing? We consider the issue of cost. Here we pose the question: what was the average number of tests per trial? Students explore a comparison between using paired testing versus just doing individual testing. In the case of 25%, and looking at both their own trials as well as those of their classmates, they will most likely find that in a 25% infected population, paired testing is a better choice. One of the key concepts developed in the lesson sequence is expected value. Through multiple activities, students explore the connection between average and expected value. Expected value is an essential tool for quantifying the benefit or loss that comes from paired testing. Next, we ask students to consider a population where 50% are infected, again using simulations with pasta. In this scenario, it's more likely that 3 tests will be needed rather than 1 test, and therefore pooled testing does not make sense. With this result, we can ask: for what infection rate is paired testing more efficient? And we can invite students to evaluate the pooled testing tool using expected value and the average number of tests per trial for a range of different infection rates. We expect that students will determine that somewhere between 35 and 40% there's a divide. They might also recognize that with random trials, they can't precisely identify that divide. The next big idea in the lesson sequence is to consider paired testing with a more theoretical and then abstract approach. To do this, we introduce geometric probability, and we again start with the case of a 25% infected population. Shifting to look at the abstract case of a population with an infection rate of P, we continue with the geometric probability model. This takes students to a quadratic model. This is part of what we find so exciting about this lesson sequence. Teachers and students are used to rockets, falling balls, and fenced sheep as their applications of quadratic models. But paired testing for a virus has the potential of being a much more engaging hook and start into quadratics. Finally, we create a graph to better understand the relationship between expected number of tests and the percentage of the population infected. Using that graph, Teachers can work with the students to explore what different points along the graph mean in context. Students can then consider how the graph can help them to answer the question, when does paired testing make sense?